Alright, now we are getting on to differentiation. So, we are going to be getting into the main concepts behind differentiation and how you can apply them. Remember, this is really what you need to be paying attention to for Year 12 content. So, this is a quick snip of topic 4 from your syllabus. So in this topic, you need to understand the basic concept behind average and instantaneous rate of change. Then you're going to need to know how to estimate a limit or an average rate of change. Then what you're going to do is actually differentiate power functions and polynomial functions from first principles, and then interpret the derivative as the instantaneous rate of change and as the gradient of a tangent line off of a function. So this sounds like a lot, so let's get started. So starting with rates of change. So rates of change tell us how one quantity varies in relation to another. So a key clue that tells us that we're dealing with a rate of change is when we have the word per, as in meters per second. So as an example, speed is a rate and tells you how your distance has changed over a period of time, such as 4 meters per second. Your distance has changed by 4 meters over a period of 1 second of time. However, not all models are linear, and so determining how they are changing is not so straightforward. And from here, we actually have to move into the field of calculus, which is a lot of what Year 11 and Year 12 is on. So, as an example here, we have a constant rate of change measured here, because for every few seconds that we jump across, distance is changing by the same amount, right? When we have gone by 2 seconds, our distance has changed by 2. When we've gone by 4 seconds, our distance has changed by 4. So for every second, we are moving 1 meter. However, in this example here, our curve is actually bent, right? It's not just straight, which tells us that our rate of change is not constant because it's a little bit steeper here, so our rate of change is higher, and then it's actually a little bit more flat here, which tells us that our rate of change is lower. So here we have a constant rate of change, and here we have a variable rate of change. So our first situation represents a person walking at a constant speed of 5 kilometers per hour. And the second situation shows a varying change in speed, initially rushing up to a higher speed and then gradually slowing down. So this might be an example of if you're running a race and you initially start the race by sprinting and going as fast as you can, which is this steep part here, so your distance is increasing more for every second passed. And then when you get to over here, your distance is not changing so much because you've slowed down. So, constant rates have a linear function, while variable rates have a non-linear function. And the rate of change is given by the gradient of the function. So, let's move on. What is the gradient for linear functions? Does it stay the same? So the gradient for linear functions is constant. And this is why, when we're looking at the equation for a linear function, y equals mx plus c, our gradient is just m. It does not change. How do we determine the variable rates of change? We need to calculate what the gradient is at any particular point on the graph, or in other words, how steep the graph is at any particular point. So let's have a look at a few examples of this. What I'd like you guys to do is identify whether the following graphs show constant or variable rates of change. So pause the recording, have a go at this, jot down your answers, and then check your answers when we're going through them together. So, part A is a variable rate of change, B is constant, C is variable, D is constant, E is constant, F is variable, G is constant, H is constant, I is variable, and J is constant. So as you can see, all of these straight graphs are constant, and all of the curves with even a little bit of curvature, where they're not straight, are variable. So, there are actually two ways that we can figure out a variable rate of change. We can calculate the average rate of change or the instantaneous rate of change. So the average rate of change tells us, what it is generally over a certain period. It's not usually going to be exactly right at a certain point in time, but it'll be pretty generally what you've traveled. An example of this might be if you run really fast at the beginning of a race and then run slower towards the end, your average rate of change, if your beginning pace is 8 meters per second, and then after that you slow down to say 5 meters per second, your average might be say 7 meters per second, right? So it's not really correct at either point, but it is the average of all of the rates of change over a certain period. Your instantaneous rate of change tells us what the average rate of change is at a particular instant, at a particular moment, right? So, let's look at calculating the average rate of change. So, consider a sprinter who covers 100 meters in 10 seconds. The average rate of change, right, is going to be 10 meters per second, because we just divided the distance by the time. However, as you can see on the graph, they actually ran faster at the beginning. So even though the average rate of change is 10 meters per second, that is not necessarily what the rate of change is going to be at any given point, because right at the beginning here it's going to be steeper, and up here it flattens out. Now, looking at the instantaneous rate of change. So this calculates the rate of change at a specific point. So, why can't we simply just use the gradient equation, right? The delta y on delta x. That is because we are looking at only one specific point. So, if we have a curve like this, and we want to find the gradient, say at this point here, we're only looking at that point. So we can't pick our 2 points to find the gradient, right? Because we're only looking at 1 point. So, the rate of change at a point is given by the gradient, or the gradient of a tangent at that point. So, have a look at this. If this is a straight line that has the same gradient as the curve at that point, the rate of change is going to be equal to the gradient of that tangent. So, we can find the gradient at a specific point by finding the derivative, right? And this is what we're focusing a lot on in year 11 and year 12. And we can find the derivative using either first principles or by formula. We're only going to go over the formula today. We're not going to go over first principles. And we use this extensively in year 11 and year 12. So make sure you spend time on this concept, because we'll come back to it a lot. So, in year 11, you're going to be deriving polynomials, which is your typical kind of parabola, cubic kind of function. And then in year 12, you get onto different types of functions, such as trig functions, or exponential functions, or log functions, right? But in year 11, you're only going over polynomials. Alright, so let's go over deriving polynomials. So, this is the formula that we need to apply to derive polynomials. This one is in your formula sheet, so don't worry too much about remembering it. So if our function is equal to x to the n, our derivative, which we denote by f dash x, that dash represents that it's the derivative. What we're going to do is we're going to take that power n out the front, and then we're going to have a new power which is going to be 1 less than our old power. If we have a function that is ax to the n, so we have a constant a out the front, what we actually do is we do exactly the same procedure, and we actually just leave the a there. So something you'll learn to remember is that if you have a constant, it just drops down from the original function to the derivative. So as you can see, just took that old power, left the a there, and then minus that new power by 1. If you have a function that is just equal to a constant number, there is no x in there, it's just c, the derivative of that is 0. Alright, let's get on to applying this. Again, pause the recording, have a go at this before we go over the solutions. So, let's differentiate these functions. So our differential here is going to be y dash equals, we're going to take that old power down, leave the x there, and then minus our new power by 1. Same thing here, we're going to leave that 3 out the front, we're going to take that old power down, and then minus the new power by 1. So we're going to get 6x. Here, we're going to leave that out the front, take our old power down, minus our new power by 1. Anything to the power of 0 is just 1, so this just leaves us with 5. We're going to leave that constant out the front, multiply by our old power, minus our new power by 1, which gives us 6 on 5x. Alright, now let's get on to some more complex differentiation. So, here we want to understand the concept of the derivative as a function, and then just get into some more complex derivatives where we have some sums. So, the derivative of y may sometimes be written as y dash, similar to the function notation. The most common was to indicate the derivative of y is y dash, and the second derivative as y double dash, and so forth. So with function notation, to identify the value of the derivative at a specific value for x, we write f dash value. So the value of the derivative at x equals -3 is written as f dash -3. So let's go through an example. Here we want to calculate the gradient function for f of x is equal to 5x cubed, and then we want to calculate the instantaneous gradient at x equals 3. So our derivative is going to be f dash x. We're going to have 5 times 3x squared, which gives us 15x squared. then we need to calculate the instantaneous gradient at x equals 3. So we're going to have f dash 3. We're going to sub in 3 for x. So we're going to have 15 times 3 squared, which gives us 135. Alright. Now let's get on to the differentiability of a function. So this tells us whether we can actually derive a function. So, for an equation to be able to be derived, it must be a continuous function. So have a quick think about what is a function, how do we test for functions, what is a continuous function. So, remember, a function is a equation that when graphed passes the vertical line test. So that means that if we draw a vertical line on the graph, it will only ever hit our equation once. So if we have a function like this, this would pass the vertical line test because every time we draw a line down, it only hits the function once. However, something like a circle, if we draw a vertical line down, would hit twice, which means it does not pass the vertical line test and so is not a function. So, what we previously said is that for an equation to be derived, it must be a continuous function. However, this definition is not sufficient. So our new definition is to test whether a continuous function is differentiable at a point x equals a in its domain. The derivative from the left of x equals a must equal the derivative from the right of x equals a. Why? So the derivative function has a limit definition. And a limit exists only if the limit from the left equals the limit on the right. So this means that only smoothly, continuous functions are differentiable at x equals a. So what this essentially means is that there's no sharp points. So when is a case that we might have sharp points? Is a hybrid function or a step function. So in this example here, we have a hybrid function. As you can see at a, we have that sharp point. And that means that at that point, our graph does not have a derivative, right? So, as you can see, we kind of have two different functions, right? We have the linear function on the left and the linear function on the right. So, the gradient from the left does not equal the gradient on the right. So our gradient here does not equal our gradient here. As an example here, we are given a function and we need to test whether the function is differentiable at x equals 1 and then give the rule for the derivative of x stating its domain and sketch the graph of the derivative of x. I'm not going to go through this one just now because we only have a few minutes left, but I really would recommend you guys having a go at this when you download the slides. Alright, what we are going to quickly go through is just a few of the other questions that we have available on the slides for practice. So we have a few harder differential questions. So these are slides 52 to 54. If you would like to check your answers, make sure you type these functions into Desmos and then ask it to find the derivative, and you'll be able to check if you got the right answer.